Hi guys, so Paul here again. So in this last section of the lecture, what we're going to do is look at how we do multi-layer perceptrons in KNIME and just some practical considerations about how you can run them. There's a few, neural networks tend to be a little bit fussy about things, so let's just talk about a few of those aspects. So there's a couple of different ways to use multi-layer perceptrons in KNIME. And the easiest approach is just to use the RProp MLP learner. RProp stands for Resilient Propagation. And then there's a learner and predictor, just the same as we've done for most of the other classifiers. So it acts similarly to the other learner and predictors. So your training set will go into the MLP learner, and then the model is output from the blue square, and then the predictor is used to make predictions. There's a really nice aspect about RProp in that it doesn't require us to set a learning rate or a momentum, so it's much easier to set up the neural network. So just a little bit on RProp, or resilient propagation. So there's a really nice paper that you can read from 1993. You can find on the internet, and it goes into how RProp works. In a nutshell, what it does is it directly adjusts the weight step based on the local gradient information. So what it does is it adds an update value, a weight update value, for each weight in the neural network. So there's a weight update for Wij, and there's a different weight update for each weight. And the idea is to change the weight update based on the sign of the partial derivative of the error with respect to the weight. So the weight update's essentially like a learning rate for each neuron. So given the partial derivative of the error with respect to the weight, so that's what backprop pushes back to do the credit assignment. First off, we look at the update value for weight ij. So if the sign of the partial derivative changes from last time, that means it's jumped over a local minima. So it means that the surface is a bit curvy, so we slightly decrease the update value. If the sign doesn't change between the last partial derivative with respect to the error and this one, then we know we're in a smooth region. So that means that the update value can be slightly increased. So the idea is, as we keep on going on smooth areas, the update rate keeps on increasing, so it learns a bit faster. But as soon as the space starts to get choppy and curvy, then the learning slows down. So that's our update value. The next thing is the weight value, the weight itself. So if the derivative was positive, i.e. the error is increasing, then we decrease the weight by the update value. If the derivative is negative, i.e. so the error is decreasing, then we're going in the right direction, so we increase the weight vector by that update value. And if the derivative changes sign from between the last update and this update, then we've sort of hit a hole, and we need to reverse the last weight update, so it sort of backtracks. So it automatically speeds up or slows down the learning depending on what the surface looks like. The other set of nodes in KNIME that can be used to build the multi-layer perceptrons are the ones that come from Weka. So these ones might not be installed in your version of KNIME unless you've installed the extensions. So you find them in the Weka folder. So it's multi-layer perceptron, and then you use the Weka predictor to do the prediction. So the Weka one just uses standard backpropagation with momentum. So you need to set a learning rate, the eta, and you need to set a momentum. It has default values. It can tend to be a little bit sensitive to these values. What's really nice about it, there's two nice things about it. First off, you can see what the neural network looks like. And second of all, you can train the neural network until the error on a test portion of the data increases. and that's really nice. You can't do that with RProp. That said, it's a lot harder in my experience to be able to set the parameters for this one. So you'll often see that when you set the parameters, it'll just output one value, so it'll just predict everything as with the one class. So this is an example of what the GUI looks like for the Weka multi-layer perceptron. So you can see here, this is just for the standard iris dataset that we looked at before. So you can see the 4 inputs: sepal length, sepal width, petal length, petal width. And also the Weka one allows you to normalize this by default. And then the outputs are the 3 classes: Setosa, Versicolor, or Virginica. And you can see that for the one that we've set up here, we've got 2 hidden layers, both of 2 neurons. And in the Weka one, you can run it for just a number of epochs, and you can run it in this interactive kind of mode. You can see there's a learning rate and a momentum. And eventually you accept the neural network and then it will train. So with either type of node, either the Weka one or the RProp, you need to be thoughtful about how you get the data in and out of the neural network. The benefit is that generally with artificial neural networks, given enough data and other considerations, they'll generally produce fairly accurate models, but of course they're black box. You can't see how it solved the problem. So let's look at some of these considerations. The first one is, how do we get the data in? Well, neural networks only accept numeric data. So if we think about the 2 major types of data that we have, categorical and numeric, then they require different treatments. So because we need to put numbers in, we need to convert the categorical to numeric. So there's a couple of approaches for doing this. One way that you might think of doing it, let's say that you have gender, and you might say 1 is man and 2 is female. Or you might have three different possibilities, well, not for gender, but 3 different possibilities for an attribute, and you just code the first one as 1, the second as 2, the third for 3. That tends not to work very well. The reason for that is because you're imposing an ordering over those 3, over the attribute values, and that doesn't necessarily match to reality. And if you impose that ordering, then the neural network, if it's not a good ordering, the neural network needs to get rid of that ordering and unlearn it. So instead, a better approach is to use something called one-hot encoding. So here's an example, because remember we're doing our generally, okay, let me put it a different way. So the attribute value that's categorical, you end up having, instead of 1 attribute or 1 neuron going into the network, you have 1 neuron for each of the possible values. Essentially, we've talked about it before as binarizing. So, but in neural network language, it's usually called a one-hot encoding. So, for example, with the different states of Australia, New South Wales would code as 1 and then 0 for all the rest. ACT would be 0 for the New South Wales flag, and then 1 for the ACT, and then 0 for the rest, and so on. And that typically is a better approach to coding the inputs into your neural network if they're categorical. The other approach, that's if they have no relationship. So we can't say that Tasmania is better than ACT or ACT is better than New South Wales. That it's not an ordinal attribute, so it doesn't make sense to create an ordering. Sometimes it does though. So the other example here, we have Z, P, C, D, and H. So fail, pass, credit, distinction, high distinction. There is an ordering there. It's an ordinal attribute. So it makes sense we can still use the one-hot encoding or a variation of it called thermometer encoding. So you can see that the Z has the Z flag set to 1 and the rest to 0. The pass has the Z flag and the pass flag set and then the rest to 0. Credit has the Z, the pass, the credit set to 1 and then the rest set to 0. So thermometer encoding works quite well as well. In terms of numeric data, the important thing to consider here is that the inputs need to be relatively balanced and to be in similar kinds of ranges. often either 0 to 1 or -1 to +1. And the reason for that is that otherwise the neural network doesn't understand that the attributes, what the meaning of the attributes are. So if there's a high value of an attribute compared to other ones that are in low values, the neural network needs to learn that the high is not important necessarily and needs to end up scaling them down, and it does that by setting the weights in that first layer. So you're better off to treat the attributes all as being roughly of the same importance, so you scale them to be in a similar range. It doesn't have to be exact, but in similar range. And sometimes you might do a log transform if the highest values are unknown. So for example, salary, there's no highest salary, or the price of a house, there's no highest price of a house. So you can often do a log transform just to pull the values back closer. When we want to get our results out of the neural network, it also depends on what we're trying to do. So if we're doing a classification problem, normally we'd use a one-hot encoding and have a different attribute for each of the possible classification values. And then you can either choose the attribute value that has the highest value, or you can, with some neural networks, maybe not the RProp, you can assume that you can train it until the values are within a certain range, either very close to 0 or very close to 1. Depending on which learning activation function you have for the output layer, then you need to take into consideration special things for regression. So if your output layer is sigmoid, we've already seen that the sigmoid activation function can only produce values between 0 and 1. So if you're doing a regression and you're trying to get values that are outside that, the neural network will never be able to produce it, because it can only produce values between 0 and 1 if you're using a sigmoid activation function. You can use a linear activation function, in which case that's not the issue, although I don't think that's tailorable on the RProp. So if you're using regression, if you want to do a regression and you're using a sigmoid output activation function, then you need to normalize the data so that you expect the outputs to be between 0 and 1. Also, with many different neural networks, not RProp or the Weka one, you need to choose the correct loss function for your network. And this a loss function quantifies the price that the neural network pays for inaccurate predictions. Typically for classification, you use the cross-entropy loss function, and for regression, you'd use the mean squared error. You wouldn't use mean squared error with classification because it doesn't really make sense. With neural networks, particularly the multi-layer perceptrons, not so much the deep learning neural networks that are more modern these days, but with the multi-layer perceptrons, it's really important to keep the number of neurons in the multi-layer perceptron as small as possible. You want to have as fewer neurons as possible while still being able to solve the problem. The reason for that is that every time you add more neurons, either inputs or neurons in the hidden layers, you add a whole lot more parameters. So the weights of the parameters. So if you add a neuron to the first hidden layer, you're adding a weight for every one of the input neurons plus the bias. So one neuron could add many, many parameters. The more parameters you have, the easier it is to overtrain the network, and it won't generalize to the test set very well. And categorical inputs cause particular difficulties in this case, because when you have your one categorical attribute can turn into many input neurons, because you're having an input neuron for each of the values. So they can particularly introduce the number of weights very substantially without you really realizing it. Particularly categorical attributes that are something like industry code or that kind of thing that have many, many, many types of values. You typically can't. That neural networks don't deal with that kind of attribute very well. Finally, I want to just really touch on the deep learning neural networks. This is really out of the scope of this class, but it's covered in other subjects in the major that you can do. That said, I really urge you to have a play around with them. Get familiar with them and start playing with them. And the easiest way to do that is to start doing tutorials for the major open source software packages. So I'd really recommend Keras. It's really easy to use. These are all in Python. It's really easy to use, and it's quite a nice one to get used to. It hides a lot of the complexity. Underneath the complexity is either Theano or more typically TensorFlow. TensorFlow is the one that is the deep learning neural network package that Google open sourced. The other one you might want to play around with is PyTorch. So PyTorch is sort of a competitor for TensorFlow. And the other package I didn't put on the slide, but if you're using R, you can use H2O. That has some deep learning neural network software. Again, it's out of the scope of the subject, but really fun to play with and exciting and more cutting edge. And that's it for the neural networks lecture.